Example 9.3. Find the potential energy of a system of four particles placed at the vertices of a square of side L. Also obtain the potential at the center of the square. Okay, so here one square is given. This is a square. Okay, and this is the square. At the four vertices of the square, we are keeping potential energy of the system at the vertices of side L. Okay, so find the potential energy of a system of four particles placed at the particles. Okay, so then at each vertices, if we are keeping the masses m, and here is also m, and this is also m, and this is also m, and the side of the square is L, then find out the total system potential energy. Okay, so potential energy formula we already know, that is equal to PE is equal to G capital M small m by R. Sorry, here it is minus. Okay, so capital G is the gravitational constant, capital M is the mass of the earth, and this is particles or body mass m, and distance between them is small r. Okay, here is also we have a that kind of masses. Okay, so here is also we have a two masses like that. Here between these two mass there is a gravitational force, and between these two masses also gravitational force, sorry, potential energy, sorry. So here potential energy between these two masses means here also potential energy between these two masses, and it about a distance is L, and between these two masses, and between these two masses, and between these two masses. Okay, so then there are total potential energies are 4. Okay, 1 and 2 and 3 and 4. Okay, so if you are considering these are the two masses, then from L distance from the this mass to here there is some potential energy, and from here to here another potential energy, like that. So we have a totally 4 potential energies. Okay, so then and also two more also there, and this is the diagonal between the these two masses, and here is also another diagonal, this is also another mass, means between these two bodies also we have a potential energy, and this is the distance between these two masses is equal to root 2 L. Okay, and this is also how much, root 2 L from here to here. Then total we have a 6 potential energies. So in that the 4 potential energies, then I'm writing here total potential energy of system. Okay, I'm writing at one place all this. Okay, that is potential energy of the system is equal to, so these are the 4, so that's why 4 of minus G into one mass and another mass, that is G m by distance between them how much, L, and the distance is L. Okay, and plus of, then there are two these diagonal, between these diagonal we have a potential energy, that is equal to minus G small m and another m, mass and mass, by distance between them, that is equal to root 2 L. Okay, this is the total system potential energy. Okay, so which is equal to, this is 4 of minus G m square by L plus of this is also minus G m square by m into m square by root 2 L. Okay, so from this we can take the common, minus G m square by L, minus G m square by L. okay, that is equal to, this is 4, okay, so plus here it is equal to 1 by root 2. Okay, so then this is equal to minus g m square by L, and this is if you are taking the LCM, this is 4 root 2 plus 1 by, and this is root 2. Okay, so this is equal to 4 root 2 1 minute. So here we can take the, okay, so here this is 2 because we forgot it. So we have a 2 system. This is the one and this is the one. Okay, by 1 it is gmm by root 2l, and by this 2 another one is root 2m by gl. So then it is equal to 2, and here is also we have a 2. Then from this 2 and this 2 we can take the common, so it will be like this. Okay, so here we have a 2 by root 2, and this is 4. From that 2 also we are taking common, minus 2g m square by L, and this is equal to 2 plus 1 by root 2, and this is equal to minus 2g m square by L, and it is equal to 2 root 2 plus 1, or it is also write down like this. This is equal to 2 root 2 plus 1 by root 2. Okay, so then this is equal to minus 2g m square into, so this 2 we can write root 2 into root 2. Okay, or after solving this totally, we don't need this. That is equal to how much we got? That is equal to 5.41 minus 5.41, okay, into, okay, so that is 1 minute please. Okay, this 2 and this 2, okay, and that is equal to how much? Minus 2 minus 2 gm square by L, and into, this is 2 root 2 plus 1 by root 2, and that is equal to, this 2 we can also write down, that is root 2 into root 2 gm by L, and it is equal to 2 root 2 plus 1 by this is root 2. 1 root 2 1 root 2 cancel, and this is equal to, so this is root 2 into root 2. So after calculated, we are getting, that is minus 5.4 1 minus 5.41 gm square by L. This is the potential energy of the total system. Okay, and also should be find out the potential at the center of the square. So potential at the center of the square means this is the center of the square, but there is no mass. So no mass means there we have to find out the potential. Okay, so potential means it is the characteristic of the position. So means by this mass there is some potential here, and by this also here one potential, and by this another potential, by this another potential. There are 4 possibilities are there. Okay, so means where we want to find out the potential, there we don't keep the object. Okay, here there is no mass is there. Okay, so that's why in our formula also in this formula, we are neglecting this mass because we are not keeping when we are finding the potential. Okay, so then potential at center of square, that is total potential PE is equal to, that is minus 4 capital G, and mass of the one is m, by distance is equal to how much from here to here, total diagonal is equal to root 2L. Okay, then from that half is nothing but here 2 root 2 root 2 by L by 2. Okay, so up to here it is root 2 by L by 2. Okay, so then it is equal to, how we can write it is, it is equal to minus 4 into 2, which is comes into the numerator, that is capital G small m by root 2 L. Okay, and that is equal to, this 2 we can write root 2 into root 2, so minus 4 into root 2 into root 2, that is Gm by root 2 L. Okay, 1 root 2 gets cancelled, and it is equal to minus 4 root 2 Gm by L. This is the potential at the center of the square.